find me at the end of the day or tomorrow. My office is 108 just like this. Okay. It is the 27th. Thanks very much.
All right, let's get started. So, John Kelner will tell us about solving Laplacian systems. I mean, solving sparse diagonally dominant linear systems is sort of like one of the problems, that a lot of the CPU time in the world is devoted to. Someone told me a long time ago that in applied domains, whenever anyone is solving a linear system, it's actually just a Laplacian linear system. And at least in my personal experience from talking to people from other departments, what's that?
Yeah.
I think you actually just cut out like all my intro slides. So it's so much more credible coming from not me, right? Continue.
Thank you, John. In any case, so the field has undergone an amazing transformation in the past 10 or 15 years, and just when it looks like it can't get any more amazing, it does. So John will fill us in on the background and the state of the art in the sequence of the next 3 lectures.
Thank you. So today I'm going to start, and tomorrow there'll be 2 more lectures, and they're going to be broadly about solving Laplacian systems. And electrical flows really won't surface today, but they'll surface in the next 2 lectures. And before I start, I think I'm going to take the chance to get a little bit of a high-level picture. So before I even get to Laplacian systems, I kind of want to say at least why I got into this general direction. And then I'll keep my pontificating brief, and I'll get to actual math fairly quickly. So the very high-level picture of what I'm interested in here is really what I think is kind of an incipient convergence between graph algorithms and numerical scientific computing. So if you kind of look at the last, I'm making up words and so let me define them. So I'll say graph algorithms, questions about flows and paths and cuts. And we'll talk, and sort of if you look at the main fast algorithms for a lot of these problems as of fairly recently, the best algorithms for almost all the problems that we know were very much discrete combinatorial algorithms, path by path, flow by flow, edge by edge kind of approaches. And then if you kind of flip over the numerical scientific computing side, a lot of the questions and algorithms tend to be very much continuous. They ask about matrices and computational linear algebra and differential equations. And for those, a lot of the techniques, essentially all of the techniques that are used are very strongly continuous numerical techniques. And what's happened very recently is, well, what's happened less recently was I think the disciplines have sort of diverged. And from my perspective, I think that they should reconverge. And in the last maybe decade or so, what's become clear is that they've been facing very similar challenges on a fairly concrete level. Like not just sort of at a high level of we need to solve big things, but on a low level of there's actually these very deep mathematical connections between a lot of the core objects that one studies in the 2 fields. And what's been emerging is the hope of using techniques from one of these fields to help the other, and hopefully letting them sort of reconverge. So if I were to kind of start off, I guess it's good to start public recorded lectures by making sort of overly aggressive assertions. So my kind of broad vision here is I think that there should be a sort of convergence of graph algorithms and numerical scientific computing, hopefully speeding up things on both sides. And if you put my kind of high-level goal here, it would be to, I think where this will be in a small number of years, hopefully, and what Alexander will talk more about tomorrow, is that I think these connections will hopefully eventually lead to a good chunk of the algorithmic problems on both sides being solvable in nearly linear time. So that's the sort of aggressive high-level goal. It's take your favorite graph algorithms or your favorite numerical linear algebra problems, and that should come with sort of the caveat that on the scientific computing side, I don't mean solving general linear systems, I mean solving ones that actually exist. So ones that sort of show up in practice, which are very structured. And my high-level goal of this, for me at least, is that to get sort of the main questions on both sides to be in nearly linear time. And as a field, I think the theory of computing community in the last maybe 10 years has made a lot of progress on that. And what I'm going to talk about in these lectures is one facet of this. So I'm going to describe one instantiation of this vision that I think has been a proof of concept that this actually plausibly could go somewhere. And that's also how to solve Laplacian linear systems. So linear systems where the matrix you're using is a graph Laplacian. And I'll show how to solve those in nearly linear time. OK, so I'm going to give a very brief why solve Laplacian systems, though I guess James kind of covered it for me. Broadly, they appear a lot. They've appeared in scientific computing as one of the kind of core objects that one studies from finite element settings. They also show up for things we'll actually exploit. They're very strongly connected to the behavior of electrical circuits. And they've also had a lot of applications in a whole bunch of other fields, in machine learning and random processes and image processing, et cetera, et cetera, et cetera. Another kind of thing that's been starting to emerge recently has been that some of the algorithmic problems on the graph side that we really don't want to solve linear systems necessarily, but want to solve other basic linear algebra problems. So eigenvalues and eigenvectors, or for clustering problems, or matrix exponentials and heat kernels. And it turns out that you can actually use the ability to solve Laplacian systems to solve these problems quite well as well. OK, so that's one motivation. I guess the other one, the one that is more up my alley, is they've emerged as a very powerful new primitive in algorithmic graph theory. And I'm really not going to talk about their use as a primitive, but other people here have or will. And what's happened is that kind of the asserted convergence at the start of this lecture, the assertion that you can use tools from one to speed up the other, has actually gone both ways. So there are these very deep connections that we'll exploit in solving Laplacian systems that let us use the graph theoretic properties to control the linear algebra to make fast linear algebra algorithms. But it turns out that you can actually use these connections the other way. And now, so you're going to use the graph theory to speed up your linear algebra, but then once you have fast linear algebra, it's been used recently to solve a whole bunch of long-standing open barriers, to get past long-standing algorithmic barriers for a whole bunch of problems. So max flow, multi-commodity flow, spanning trees, sparsifying graphs, which we've heard about from Nikhil. So in particular, my first motivating application, I guess, will be Nikhil's first talk, which solves Laplacian systems and asserts that you need to solve that uses the solution to Laplacian systems to sparsify graphs. That's much faster if you can solve Laplacian systems quickly, but also a whole bunch of other problems, and Alexander will talk about a bunch of those tomorrow. OK, so that's my super high-level vision. And the plan for the lectures is as follows. So today I'm actually really going to only barely talk about Laplacians. So today my goal is going to be to present the background from very standard classical iterative methods that will be used in the other lectures. So James, when he was asking me to give these lectures, he asked to make these very self-contained. And so the hope is that if you have never seen an iterative solver before, that by the end of today's lecture you'll be able to see the next lecture, which will use them to solve Laplacian systems. I'm then going to do in the next two lectures so James also said don't get over-aggressive. You don't have to present a whole Laplacian solver. And so I'm going to present two of them. Today is going to be background on iterative methods. Number two is going to be one approach, which is the one that I'm going to follow an algorithm due to Kudus, Miller, and Peng. It loses a couple log factors from some of particularly their more recent work, but it's got this very clean, simple picture, and I'll say a few words about how to improve it, but it's actually going to be pretty close to the state of the art, and I will get most of the algorithm into the second lecture. So I'll sketch some details, but give you the high-level picture. And it's going to be based on something I'll describe how it sort of works, which is recursive preconditioning. And then in the third lecture, I'm going to talk about a recent algorithm that I wrote with Aaron Sidford, Lorenzo Orecchia, and Zoan Zhu, which is on kind of how to avoid the machinery from the first two lectures. So the first two lectures, I'm going to develop sort of classical iterative methods and show how to use them to do preconditioned recursive preconditioning for Laplacian systems. And the third lecture, I'm going to show how to avoid all of it and get an algorithm that actually doesn't use any recursive preconditioning at all. That being said, I should say that it has, I think once we sort of see all of them, they're very strongly related in some ideological note, and a lot of the motivation for what it does comes from the ones right before it. And so I think what I wanted to do was sort of present both collections of methods, also because I think that the methods from each of these generalize in different ways. So the ones from sort of the second class has recently been used for max flow problems. The one for the third one, I think, will be used for some things in other settings, and is a sort of clean, simple, and self-contained algorithm that will let us solve Laplacian systems really fully contained in one lecture. OK, so that's my setup. Now I'm going to kind of put my apology in here. And the general apology is that we're doing numerical analysis, and I'm going to not. So a lot of the stuff that one does with everything I'll do today, it works really cleanly mathematically if you do everything where you pretend that you can just do real arithmetic, and you really can't. And I think it kind of hides the ideas if you write the numerically stable versions of some of the things I'm going to write in the first cut. So what I'm going to do is I'm going to write things that are correct assuming infinite numerical precision, and just because they have the sort of clean mathematical structure that makes what's going on actually kind of make sense. And I'll say a couple words, but I'll probably largely brush under the rug the right way to implement them so that you don't do something horribly wrong. And I should say that for each of the things I talk about, especially for the Chebyshev method, which we'll see today, which involves polynomials, there's sort of a right way and a wrong way to implement it. And if you kind of blindly apply the polynomials I'm writing down, it's very much the wrong way. And you can write things that are mathematically equivalent in the sense that you're going to be, if you pretended you had infinite precision, you'd be computing exactly the same things, but organizing the computation in a way that doesn't horribly blow up your stability. And it turns out that the good ones are actually quite stable, and the bad ones are very not stable. And I'm going to largely brush that under the rug, just sort of for clarity. I'll be happy to answer questions about it or kind of say what we're doing wrong. But I guess the main point here was I'm not writing something that's numerically stable. If you ever implement it, you should. And numerical analysis is a field. Like, I'm ignoring it almost entirely in these lectures, but it actually needs to exist to make these into real algorithms, and it actually can be made to work. You know, these are not inherently unstable. They're just presentationally unstable. OK. Oh, and the other thing is just, in general, feel free to, if you have questions, interrupt me, cut me off, etc. OK, good. So moving right along, today's lecture is going to, I think, really not make it past 1980 or so. But I want to talk about just sort of general methods for solving linear systems. So my main goal here is just to give you kind of the high-level picture of iterative solvers. And I guess the main question we're asking is, how do you solve AX equals B? And from a CS theory side, I guess we know the answer is that you can do an O of n to the 2.373 time using appropriate tensors. We're not going to answer that question. We're going to instead look at structured linear systems and ideally sparse ones. And you know, kind of the theoretical answer, the answer that you say, if you just wanted to convince yourself algebraically that there's a solution, you know, it's kind of multiply by the inverse of the matrix, right? In real life, this is very bad, right? And there's a couple reasons. One is it's, of course, quite slow. It, at best, is n to the 2.373 whatever, which we're not going to be able to tolerate if you have a graph with a trillion vertices. Also, the real problems are sparse, right? The problems that show up a lot, if I have a trillion vertex graph, it's almost never dense. And if you write out the inverse of most sparse matrices, you do not get sparse matrices back. And if you're just writing out inverse and multiplying, you don't get to exploit that. So you pay for something that has no benefit from sparsity. Also, there are these precision issues that I'm acknowledging exist and then ignoring. A better answer sometimes is, I guess, Gaussian elimination, which is the right way to do multiply by A inverse. Or maybe I should have said equivalently, you know, computing LU factorization and back substitute. These are not abstractly always bad ideas, right? They're good if you have sort of an unstructured problem that's dense. If I give you a dense matrix that you want to solve a linear system with, and you know nothing about it, that's actually not a terrible thing to do. And it's also nice in that when you compute these LU factorizations, you can solve multiple linear systems. Once you've done all your work to get this factorization, you can solve a bunch of right-hand sides very easily. OK, so this is not something I want to universally rule out, but it won't be the goal for the lectures. And the reason is that the things we're going to mainly kind of work towards are going to be Laplacian systems. So think graphs give Laplacians that are sparse. We want to solve it in much better than even n squared time, right? Even the time to just write down the whole inverse. OK, so, and kind of more generally, in practice, very, very rarely are problems dense and unstructured. They tend to almost never exist. And so getting a handle on how to exploit sparsity and structure is certainly sort of a fundamental goal. OK, so for sparse systems, the main technique is iterative methods. And excuse me. So I guess there's many ways one could sort of broadly define iterative methods. For this, I'm just going to think of it as anything that's iterative. So the idea is instead of trying to exactly solve something like Gauss elimination or LU, you're in this infinite precision world. You're just exactly solving the system. Here, think you start with a crude guess and repeatedly improve it. And ideally, your steps will be very cheap, both in time and memory. So you don't want to write down the whole matrix, like a whole matrix every step. And also, you want it to be very fast. And you should think of it as like each step should be a constant number of matrix vector multiplications plus some other less expensive stuff, like some vector additions. And the hope here is that if you're doing only matrix vector multiplications per iteration, that you can exploit the sparsity. Because if you multiply matrix times vector, sparse matrices are certainly faster to do that with than dense matrices. The other thing that's going to show up in these is that if I give you Gaussian elimination, how long it takes has nothing to do with the matrix, right? Whereas if I'm giving you these iterative methods, then there's some numerical property of the matrix that strongly dictates the behavior. And it's often in essentially every case I can think of other than lecture 3 in the series and things like it, it's going to be dictated by the eigenvalues and singular values, and arguably even the method. OK, so that's what we'll talk about today. I should apologize. I see some people in the crowd who I know already know everything I'm going to say, but I should apologize to them. But OK, let me now kind of give you the high-level ideas. OK, so first, let me start with some notation and assumptions. We're going to solve AX equals B. And for the rest of today, every matrix I ever write down will be square. N will be the size. It'll be n by n. If I ever say m, you should think it's the number of non-zero entries. So for graphs, vertices are n and edges are m. All my matrices will be symmetric and positive definite. And so in particular, non-degenerate. Now this one, I guess, doesn't seem like it seems like a fairly restrictive constraint, but it's really not that bad. Right? Not all matrices are positive definite, and not all of them are symmetric. But it's really not the end of the world. And the reason is that you can use a black box solver for a positive definite symmetric system to solve all linear systems, or at least all non-degenerate ones, just by sort of a silly little algebraic trick. Right? If I can solve symmetric things, then I'll just multiply both sides by A transpose. And I can solve A transpose AX equals A transpose X. So this is not a horribly generality-losing assumption. But it does, I guess, come with some simple question first, which is that I motivated this by saying sparsity. And I just, A transpose A won't be sparse. But note that I don't, in everything I do, I'm only going to need to multiply by the matrix involved. So I'm never going to actually have to compute A transpose A. I'm just going to have to multiply by it. And so that you just have to multiply by A and then multiply by A transpose, so you can still exploit sparsity. OK, so other notation. Unless I say otherwise, lambdas always mean eigenvalues. I'll sort them in order. So lambda 1 is the smallest, lambda n is the biggest, and I'm assuming positive definite, so that's a strict inequality. X star is going to be the exact solution. Xi is going to... Sorry?
The right-hand side should be A transpose B, right?
Sorry?
Yeah, the right-hand side should be A transpose B.
Yes, I should. I guess there's a less interesting solution to this one. Yes, thank you. Sorry, the right-hand side should be B. Yes. Otherwise, I can do that one really quickly. OK, so anyway, X star will be the actual solution. Xi is going to be your guess in your iterative method. I'll write EI for the error on the left-hand side, so for the difference between your present guess at Xi and the actual, the actual solution X star. And I'll write Ri for the right-hand side error. Right? So if EI is the error in X and Ri is the error on the right, so it's B minus AXI, which is just A times EI. Negative AI times EI. So now there's this annoying sign convention where these negative signs pop up, and I think I consistently kept it in the lectures, but given that you can consistently keep the letter B, I'm not that optimistic. OK, so the other thing I should say now that will surface later is that there's sort of a right norm to measure your error. Turns out that measuring your error in the the general norm on X, the L2 norm on X, isn't really the right thing to do. Because if A has very widely different eigenvalues, then changing X a little bit in one direction or another direction will make a very big varying difference in the right-hand side. And so instead, the sort of natural norm to use is the A norm. So if I ever write a norm as little a, it just means that instead of you measure norms by just if whatever's inside the brackets transpose A, whatever's in the brackets. So the A norm of EI is EI transpose AEI, and that's going to be the quantity that one really wants to shrink. In most of today, it won't really matter. Any norm will do, but for once we start doing preconditioning, we're going to have to be careful with this.
You take the square root of that?
Yes, I should. Yeah, so that's the square root of the norm. Thank you. Again, otherwise. So
it's the product of the left and the right errors.
yes. So yeah, I guess this should come with the additional caveat that somehow this morning I discovered my slides got badly mangled by PowerPoint. PowerPoint did not adversarially change my equations, but fixing PowerPoint adversarially changing the order that everything appeared on the screen has meant that my equations might have mistakes in them. So if so, I'm sorry. Okay, good. So let's start with our first iterative method, and then we'll see how to improve it. So the first iterative method we're going to look at is just gradient descent. And that one we know. So what we're going to do is we're just going to turn our linear system solve into an optimization problem. So our goal is going to be to minimize f of x, where f of x is going to be our error is a norm squared. Okay, at least I'm consistent. Which is, right, so we're going to take the error, we're going to square it, hopefully, and then we're going to use that as our objective function. And then we're just going to try to improve it by gradient descent. So the idea is we'll compute the gradient. If you do the algebra correctly, you get the gradient is 2 times ax minus b, which conveniently just equals the residual times 2. And note that if I make A symmetric and positive definite, as I have, then this thing is a nice convex function. It's strictly convex, so it has a unique minimum. And that happens when the gradient equals 0, which is just when ax equals b. So all I've done is rewritten my problem as a minimization. And I just said, the error is clearly never less than 0, so when it's 0, we're right. Okay, that's our setup. And then a very natural algorithm, sort of a first guess at what we'll do, is gradient descent. So find the direction of steepest decrease and just take a step in that direction. This, of course, comes with the 2 obvious questions of what direction and how big a step. The first one, gradient. The second one's a little subtler of how big a step to take. There's a couple choices. The kind of right one is line search, which means that what you'll do is I pick this direction, I have an objective function. I'll just take the whole line and look along the line for the best answer. In this case, we can actually exactly compute the right step size. So if you do the algebra out, it's easy enough to figure out the exact right step size. In the things we analyze, we're going to just we're going to change that a little bit in a way that won't affect the asymptotics, but will make our lives a little easier. Okay, so kind of filling through the instantiation of this, the gradient is just negative 2Ri. And our algorithm is just going to be, initialize it. We're going to start with a guess of 0. That's without loss of generality, because you could just replace x with x minus your initial starting value, and so you might as well start with x is 0. So our residual is b, and our algorithm is just going to be repeatedly find the gradient direction. Now note, the gradient direction is the residual, which is a kind of convenient coincidence, or non-coincidence. And then the update step is just you take your present value of x, and you add some multiple of this residual to it. I asserted you can compute the best thing to do. It's not very hard. It's this thing that we'll never use again. So this is a fully formed algorithm for solving linear systems. And it's worth noting that it does fit my description of an iterative method, right? If you notice, all we ever have to do...
Best in what sense?
Sorry?
Best in what sense?
The line search sense. So you take the line, Ri gives you, you take all alpha, so it's a line, and you take the one that minimizes the objective function along the line. It's just the restriction of a quadratic that I just solved for. Okay, so all we ever need to do is matrix vector multiplications and vector operations, right? And the reason is that, here the only one that could be subtle is the Ri, the step direction. But computing the gradient is just computing Ri. Computing Ri is just computing ax minus b, right? So the gradient does nicely line up. And so all we ever have to do is if I give you my present value of x, you multiply it by a, subtract it from b, repeat. So what we have now is actually a well-formed iterative method. We just have to convince ourselves it doesn't take too many steps. And the nice thing to note is that it's a constant number of matrix vector multiplies per iteration. And so at least we have some hope of a good algorithm. Okay, so now let's see how well it does. And for this, I'm going to slightly simplify it. I'm going to analyze what's essentially first-order Richardson iteration. And all I'm going to do is I'm not going to do line search. I'm just going to fix one alpha and use it for all the steps. So you're going to choose alpha kind of in advance as a function of the matrix, and then you're not going to line search every step. You're just going to use that same alpha over and over. And when we do the analysis, we'll see what the right alpha is. Now, it's by the way worth noting that this is really mainly to sort of preface the stuff I'll talk about later. It's not that hard to analyze this even with the line search, but this is one that will generalize a little more cleanly. You can actually think of the line search as behaving more or less as if you just, it will be at least as good as the analysis I'm doing here. And in general, it will be the same. So if you were to think in kind of a worst case asymptotic sense, these two will behave very similarly. It is possible the line search can sometimes do much better. But you should think of it as just gradient steepest descent is more or less just picking the best alpha without you telling the right alpha in advance. So, okay, that's the main simplification. Not a huge deal. And we're just going to do some algebra with it. So note that ARI is just, alpha RI is just alpha times B minus AXI. And we're going to just kind of play with the equations a little bit and write this as I minus alpha AI times XI plus alpha B. So this was just a rearrangement of terms. Now, okay, so what we're going to try to do is convince ourselves this converges quickly. And now we at least have a nice setup for the iteration. And so we're just going to write out the error terms. This really is not a super deep analysis, but it will be important as we go forward. Okay, so here all I'm going to do is the only thing you could do, which is just write out what happens to the error and then hope you can see how it goes down. So if I look at the difference between xi plus 1 and x star, all I did was subtract x star from both sides. I have a formula. It's just the one above it minus x star. And now if we just kind of expand it out a little bit, we'll see we can rewrite it as follows. We'll note that b is just alpha a times x. Sorry, is a times x. So alpha b is just alpha ax. And now the point is that we can rewrite this as something very nice. We can rewrite it as this fixed matrix I minus alpha a times the error xi minus x star. So what this tells us is that if we look at the step that this gradient descent is giving us, we can just rewrite it as multiplying the error, the e sub I, by I minus alpha a. And that's convenient, because now we actually can analyze what happens to the error. Right, so this says, this is the main benefit calculationally of fixing alpha, is that this is now nice and clean. So here what we saw was that the error gets multiplied by this matrix, I minus alpha a. And so if I do it a whole bunch of times, I just multiply by the power of the matrix. And so we end up with that the error, xi minus x star, just gets multiplied by 1 minus alpha a to the I. And in order for this to be small, what has to happen is that we have to control the norm of this matrix alpha a, 1 minus alpha a. So 1 should mean the identity. 1 is the identity here. Good. Okay, so let's just see what happens. It's not that deep, right? You want to study what happens to the error, so you say matrix times vector, and you'll just bound its norm by the spectral norm of the matrix times the original starting norm. Right, and so the point here is that if this thing is substantially less than 1, then we'll get a fast convergence.
So you don't have the A norm now? Or
so this one, I put a generic norm sign because it doesn't really matter. Later, when we do things with preconditioning, the A norm, like this will be true in whatever norm you want, because we're just going to show something that's contractive. But starting later in the lecture, the A norm is the right one. So this will be true in both whatever norms we're getting.
Well, also your norm has to support that the I can come out.
Has to
Means norm of a to the power I is.
has to be a matrix.
Yeah.
norm.
Oh, it's a matrix. So it's any norm, any matrix norm, not an arbitrary. Sorry.
No, the operator norm will satisfy this exponentiation. Some other norm might not.
Right. So sorry. For Robbie's question, I was answering whether you use the identity or A as a matrix, not a generic norm. So it's a matrix. And here, so yeah. So the answer is here. You should really think A norm, but I put a general one because it's good for any matrix norm. So what happens? We now just have to convince ourselves that 1 minus alpha A has a bounded spectral norm. And when does that happen? Well, the key point that's going to emerge over and over is that we have nice symmetric positive definite matrices. What happens when you analyze powers of them or any polynomial applied to a symmetric matrix? All you do is take that polynomial and apply it to the eigenvalues. Okay, so here I have the eigenvalues of 1 minus alpha A are just 1 minus alpha times the eigenvalues. And in order for this matrix to have bounded spectral norm, all we need is for all of these to be less than 1. And how much less than 1 will dictate how quickly this thing converges. So the right choice of alpha is going to be the one that's going to make the worst case of these 1 minus alpha times lambda i's as small as possible. Right? So if I had a one-dimensional system, I could just make alpha be 1 over whatever the number is, 1 over lambda, and then solve it in one step. But what we have to do is simultaneously pick one alpha that simultaneously makes all of these things small in absolute value. And so upshot is we want to minimize the maximum value over all I of 1 minus alpha times lambda I. What's the right thing to do? It's linear. It's either going to be the biggest one or the smallest one that causes the extremal value. So we want to just pick the alpha that minimizes the max of these two numbers, of the biggest eigenvalue and the smallest eigenvalue. And the answer to that is you make them equal, and it's going to be given by 1 over their average. Okay, so I've now given you the right alpha, and we can just plug it in and get the right analysis, right? So now that we know what the right alpha is, we get the right value for this maximum, which is just 1 minus 2 lambda 1 over lambda 1 plus lambda n. That's just plugging into the equations. And when we put it together, what do we get? We get that this maximal value is going to equal, well, we can rewrite it a little bit. We're going to divide the numerator and denominator by lambda 1, and write this as 1 minus 2 over 1 plus this ratio, lambda n over lambda 1. And we're now, from here on in, going to name the ratio lambda n over lambda 1 kappa. And that's going to be the condition number of our matrix, and that's what's going to dictate the convergence of essentially everything we study. So the upside of all this analysis was that we got that the max value of this function was just 1 minus, essentially, constant over kappa. And so the number of iterations that it took was something that depended linearly on kappa, right? So if I want to make 1 minus alpha I small, if I want to make it less than some epsilon, I'm asking what do I have to raise this thing to get it to be less than epsilon. And so what is that? Well, it's like, think of this as just 1 minus 1 over kappa. So you raise it to the kappa power, you get a constant, and then raise it to a log 1 over epsilon to get whatever constant you want. So what this tells you is that in particular, this algorithm actually does have an analyzable bound, and it's not a terrible one. It says that once we put this all together, if I correctly choose my alpha, I can get this to converge in a number of iterations that grows linearly with kappa, with the condition number of the matrix. And so the main takeaway points are that this works, and that the important parameter that dictated the numerical properties was the ratio of the biggest to smallest eigenvalues. And that really should make sense in the sense that, like, if that ratio were infinity, if you had a 0, then we'd expect things to go horribly awry, right? If the smallest eigenvalue were actually equal to 0, then we really should have stuff blow up in horrible ways. If they're pretty close to each other, we're more or less trying to invert the identity, which should work pretty well. And somehow the thing shouldn't depend on a kind of simultaneous scaling of the two, because nothing changes if I just double the whole whiteboard. Okay, so that's steepest descent, and we're going to try to improve on that. Are there any questions?
Is this algorithm used? Where is it actually?
Gary? Has anyone ever used this?
It's used as a first step for multi-grid algorithms. Just do a little bit of
that's
that,
good.
and then.
So, okay, yes, so it shouldn't be your whole algorithm. There are times where I guess it's not a bad idea to use it partially, but we're going to improve on it fairly substantially in the next board. The nice thing is it's simple, and certainly the gradient descent version of it will be used a fair amount when you're not solving linear systems, but you're doing nonlinear things and you don't have the additional structure. But yes, I guess sometimes as a partial step. I'm about to improve it fairly substantially, so it's at least easy is the nice thing about it. Okay, so now what? So before I actually talk about how to improve it, I want to talk about another way of writing this whole algorithm down that I kind of want to argue that we already knew how to do this. And my assertion is really what I just said for you was that applying matrix, if I give you a symmetric matrix, you can just pretend it's its eigenvalues. And so if I want to approximately compute 1 over x by a polynomial, I'll just use a Taylor series. So I claim that so this next slide is just going to be my instantiation of that assertion. I'm going to say that really all we did was write down a Taylor series. And why is that? Well, if you expand out the recurrence, you get xk is something. It's a polynomial in the matrix applied to the vector b. And the residual is something else, another polynomial applied to b. And this is just by induction. So Now let's just kind of forget what the polynomial is and just note that what we've done is we've said xk is this polynomial that we wrote down applied to the starting vector b, where the polynomial is this thing. And what is this thing that I just wrote down? All I did is replace the capital A with a y and call it a univariate polynomial. This is just the Taylor series for 1 over y around 1 over alpha. So if you expand out the algorithm that we just did, you take steepest descent and you fix the step size, you end up with your whole algorithm really was, morally you want to compute 1 over a, so you're going to write its Taylor series to the first k terms and apply that to your right-hand side. Now why did we expand it around something other than 1 or around wherever we did? So the point was that again, we're applying this simultaneously to all of the eigenvalues, right? Like we want to kind of cover all the directions simultaneously. If it were a 1-by-1 matrix, we could Taylor expand around a single eigenvalue and get a rate of convergence that is just immediate. But we have to sort of simultaneously get this polynomial, the Taylor series, to work at all of the eigenvalues. So we're going to put alpha kind of square in the center. Or 1 over alpha square in the center, and then Taylor expand around that. So to write this out a little pedantically, we're going to say nothing depends on the basis that we work with, so we might as well just look in the eigenbasis, and then we can just pretend everything we ever write down is diagonal. I'm going to write things for 2-by-2 matrices, just because there's nothing that changes. Just think lambda 1 and 2 are min and max. And the system we're now trying to solve is that lambda 1, lambda 2 times x is b1, b2. Of course, remembering that we don't know how to compute the eigenbasis, or else there would, of course, be easier algorithms. But analytically, this is what we're looking at. If we write it in the eigenbasis, and then the actual answer x star is just, what do you want to do? You want to do 1 over lambda 1 times b1 and 1 over lambda 2 times b2. But you want to get this by applying a polynomial to the whole matrix. And so all we're really doing here is saying, let's take the polynomial, the function 1 over lambda, and we're just going to apply this polynomial, which is the Taylor series of 1 over x. We're going to apply that to the matrix. We'll simultaneously apply it to all the eigenvalues. And then what's the error term? The error term is just the error in the Taylor series. Right? It's going to be what's left over when I take the difference between the Taylor series and 1 over lambda. Okay, any questions on that?
So it's not unreasonable that when you have more eigenvalues, it's not just the first and the last one, how they're distributed, right?
Yes, and actually that's a very good point, which is that if you really understood your matrix, then you could certainly do much better, right? You could pick a polynomial that's kind of handcrafted. What I won't really talk about, but is true, is that if you use the public conjugate gradient method, it will actually have an error analysis that will really say you'll perform as well as the best polynomial that you could use to interpolate the eigenvalues, and then, which will give exactly what you said. But what's nice about conjugate gradient, and I'll say a few words about it, but not really, is that it manages to perform as well as the best polynomial without in advance having to know all the eigenvalues. What I'm going to talk about on the next slide is just a better source of generic polynomials that only still rely on min and max, but you could, of course, hope and expect to get a benefit if the eigenvalues are clustered in some nice way. Thanks. Other questions? Okay, so now what? So I've asserted that we're going to do better than this, and the question is how? How can we hope to do better than, better than the Taylor series? And so we're going to do is first just abstract our approach, and I kind of already said it. The approach I just described was apply polynomials to the matrix, so let's just write it only using polynomials. And so, and this is really just to see what we're going to do moving forward is find better polynomials than the Taylor series. And I'm just going to write out what we're doing so that we see what the properties are that we're trying to get. So, okay, so what did we really do? We really just picked some polynomial of degree k that I'll call pk of a. We applied it to b, and remember that b is just negative a times the optimal answer, because x satisfies ax equals b, or negative, yeah. Okay, so writing this out more, what do we get? We get that our error, ek, the error after k iterations, is just, we showed that what it was is you're just taking the polynomial, well, just writing it out, right? You just plug in the polynomial applied to negative ax, subtract off negative x star, and see what happens. And what you end up with is that your error is what you get by I minus the polynomial. Here it was the Taylor series applied to your matrix. And then that whole thing applied to the vector x star. And I'm just going to name this quantity 1 minus y p of y, I'm just going to call that q of y, or qk of y for each one of the iterates. So the upshot was that all we really did was apply a polynomial to our matrix, and then what that did to the actual error was apply another polynomial to the error. And what the error was we wanted p of k to equal 1 over y, and so the error we got was just the difference between y times our alleged 1 over y and 1, right? So this is just exactly what happened on the Taylor series side. We want y p of k to be 1 because we want p of k to be pk of y to be 1 over y. Instead, we got something else, and then what happened to the error was that we took this error polynomial and applied it to our original error. Okay, so, and here, note that our original error was actually x star, so we end up with an actual relative error bound. So now we can say, what do we need to do better? We need to get polynomials that make good things happen with q, right? The operator norm of this matrix qk of a is just the max over all the eigenvalues of the polynomial qk applied to the lambdas, which we could write out. It's that, and then what we did in our previous step was we just used a very natural way to approximate a polynomial, right? If I say, I give you a polynomial, I give you a function, you want to locally approximate it by a polynomial, the standard first thing one would do is just write out a Taylor series, right? I want to approximate 1 over, so pretend alpha is 1. I want to approximate 1 over x, I'll write it as 1 plus x squared plus x cubed plus x to the fourth. Right, so that's all I did is just a Taylor series. And okay, so now the question is, can we really do better? One more assertion. Once we wrote that out, what did we get as our error? We then just multiplied, if you just take your polynomial and multiply it out, you get the next term in the Taylor series as your error. That's exactly this 1 minus alpha y to the k, which was the thing that gave us our, that we needed kappa iterations, right? So we're Taylor expanding around this alpha in the middle. Your polynomial is then 1 minus omega 1 over kappa, and you have to raise it to that power to get something good. Any questions? Okay, so now the main point is that we actually nothing that we did required anything about that polynomial to be the Taylor series. And all we really needed was, well, any polynomial p, and we wanted it to make this expression small. And it's going to be a little easier to construct a q. So note that if I give you any q, it comes from a p as long as I can do that. So it's just every polynomial with first term 1, right? So every polynomial with q of 0 equals 1 is the q corresponding to some p. And so what are the properties we need? Well, first we need to know that we can still implement this. And the point here is that we can, right? If I give you any polynomial in the matrix A applied to a vector B, then there's certainly a naive way to do this, which is just I write the coefficients of the polynomial p out, and then to compute each monomial, I just take the previous monomial and multiply it by a. We'll actually see that there's a recurrence relation that's a little faster than this. So it turns out we can do something even a little better than that. We can actually just keep the last two terms and it will satisfy a 3-term recurrence. But from an algorithmic, just sort of an asymptotic standpoint, all we need to know here is that we can compute this with matrix vector multiplies by just computing the monomials, and then each time we compute a monomial, we add it times a coefficient to the previous one. Okay, so what I'm going to show you in the next couple slides is something that if you haven't seen it before, I think is kind of surprising, which is that the Taylor series is the wrong way to approximate a polynomial in this case and in many cases. And so what we're going to show is how to construct a polynomial, qk of y, that's vastly better in its asymptotics. So it's going to be a polynomial that instead of being 1 minus 1 over kappa, it's going to be 1 minus 1 over root kappa. So it's going to say that you can get the behavior of using the first k terms of the power series of the Taylor series, but you're only going to use square root of k terms in the actual expansion. So that's going to mean that if we can implement this, what we'll end up with is that instead we'll get to take a square root of our iteration down, which is a big deal, right? Like it says that however many iterations we're taking before, we're taking roughly the square root of that. So it will depend on the square root of kappa instead of kappa. Yeah.
So the degree of qk will be k, but it's implicitly always.
Oh, sorry. Yeah. So qk means the kth in whatever series I'm writing down. Sorry. I guess it's a little. There's k's and kappas. I'm not sure if they look too similar. Kappa is the condition number. K is the power. Yeah. So qk is the kth term, and so what we're going to show here is how to get a degree k, k polynomial that is much better than the Taylor series. So we'll only need to take degree root kappa instead of, but it grows with root kappa instead of kappa. So it's the square root of the condition number is the running time. Does that make sense? Questions?
So your iterations are always linear, but they only increase the degree by 1 at most.
Yeah, so the iterations in the simple implementation here is just going to be, you're just going to multiply, do one matrix vector multiply and some additions, and then compute some, and then continue. Two matrix vector multiplies. Yeah. And so it takes you k steps to make a degree k polynomial. Take k iterations, and think each iteration is, you should think sparse matrices, so think matrix vector multiply is like linear time. And so you should think that the number of iterations times n is about how long this will take in most cases. And so you want to keep the iteration count down.
But you never want to square matrices or multiply terms, because then you might lose the sparsity.
Right, exactly. So you don't want to do dense operations, right? So you're not going to ever compute the whole, you're never going to compute the actual polynomial on the matrix A, because that would completely destroy your sparsity. You're going to get it by taking your starting vector and just applying your matrix repeatedly, which is, if you have a sparse matrix, it's going to have it's going to only be linear in the number of non-zeros, not in the size of the matrix. Does that make sense? Yeah. Other questions? Okay, so now how are we going to construct these polynomials? So I guess the first question is, why would you even think that these exist? I guess, and so I'm going to kind of just say out loud a couple things about where these might come from, and then depending on how long I drone on about that, I'll vary how much I say about them. But okay, so the first question you might ask is why is the Taylor series not just the answer? Like if you take an intro calculus class, you learn the right way to approximate a function by a polynomial is the Taylor series. And my assertion is that that's not really true. And the reason is that the Taylor series is sort of an optimal point for one specific question. The Taylor series says you're looking in this infinitesimal neighborhood around your starting point, and you want to be as good as possible in this infinitesimal neighborhood. Now here, we don't have that situation. What we have is we have this range of eigenvalues, lambda 1 through lambda n, that we want to be good on. And we really don't care, we don't just care about an infinitesimal neighborhood, we want to be good for this whole sort of finite sized region. And what we're going to see is that the right thing to do, this is going to be my very crude schematic, is, very crude schematic. Let's see, I shouldn't put it back. Try to get it back. There. So, what we'll see is that kind of morally, if I want to approximate some function here, I'll make my function, I don't know, let's think what's a good picture to draw. So if I want to approximate, let's even just make our function be, something like that. If we want to approximate our function locally at right around the origin, then the Taylor series is going to do something like this. It's going to be kind of locally correct, but it'll probably globally diverge. And what the righter thing to do is if I tell you that you want to be correct in some finite region, then what you're going to do is you're going to tune your actual approximation to the region that you want to be correct over. And what it will do is instead of kind of greedily making the starting point work, it will kind of oscillate around the function, right? It will be a function that will be tuned to the region. It'll probably go horribly awry the second you leave the region, but it'll be tuned to the finite region you're trying to approximate. Okay, so that's my very crude answer. It's that we want to approximate over a finite region, not over an infinitesimal region. So you'd think that the choice of polynomial should depend on the region. The slightly more informative one is that what we'll see is that what we're really going to write down is essentially going to say use Fourier series, not Taylor series. So if you think about kind of at a caricature level, the two things we know how to approximate a function with in our first cut are Fourier and Taylor series. Fourier series are sort of shooting for a finite region, and they're vastly better behaved. If I give you a polynomial or any function on the circle, and I want to get a good approximation of the function on a circle, then we know we have these very strong convergence guarantees you get for doing a Fourier approximation, which is supposed to look like my little squiggle. Whereas if you try to do a Taylor series, you get much, much worse things for periodic functions. And so what we'll see is that in some sense, all the stuff I'm going to write down really is just the real part of a Fourier series, and that's where these things come from. That's my hand-wavy answer. Now let's actually do it. So what are the properties we want? We want it to be, so we're going to shoot for Q instead of P, just because it's a little easier to construct. But you should think what we're really doing is constructing a basis for functions that are good at approximating stuff on finite regions. So, and then we're going to see what they do. Okay, so the construction we're going to shoot for here is that we want a polynomial that's 1 at 0, and we want it to be as small as we can inside our region lambda 1 to lambda n. So now my kind of squiggly caricature is going to become that we want our function to be, we're forced to have it be 1 at 0, and then I give you this range, lambda 1 to lambda n, and we want it to be as small as possible. So I guess Taylor series do something like this, and what we're going to end up doing is going to be something a little bit more like this. So that will be our goal. And we're going to base our construction on Chebyshev polynomials. So let me tell you the properties we'll use about Chebyshev polynomials, use them to get the answer, and then tell you what they are. So Chebyshev polynomials, the properties we're going to use are just that it's going to be nicely bounded between -1 and 1. So the actual polynomials we'll use are just going to basically shift this interval to -1, 1. And so Chebyshev polynomials have one property, which is that they're very nice and well-behaved inside -1, 1, and they blow up very strongly once you leave -1, 1. So if I look inside -1, 1, they're bounded by -1 to 1, and then if I give you anything to the right of the interval, say, so if I give you, if I apply them to 1 plus a for any positive a, they blow up exponentially in k. So the kth one looks like 1 plus root, something that's like root a, doesn't matter the two, and then raised to the kth power. So they shoot off to infinity very quickly. And they turn out to be optimal for a property like this. So then once I have these, all we're going to do is just kind of shuffle things around to make the -1 to 1 become this, and make the off to infinity become this, right? So we're going to try to make the value at 0 be very big, and the value in our interval be very small.
In order to make sense here, I have to say something about the leading coefficient. Or this is very easy, right? This is very easy to do. You have to normalize them somehow. They're optimal in n infinity for normalized leading coefficient.
Right.
So what's missing from your...
Oh, did I forget to write that they're one? That they're also.
The way you write them, I think the leading coefficient is 2 to the k.
Yeah. Well, so I'm right now only. I'm writing down a Chebyshev polynomial. I'm not. They're not going to be the. This is the polynomial I'll actually use. Then the leading coefficient is going to get divided out because I'm going to transform them out. I mean, I think I wrote something that's still non. I think I wrote something that's not vacuous. I mean, I just made the L infinity norm down to be 1. Right. So all I did was just
Is it somehow the case that here coefficients don't matter so much?
So that's a very good question. That's the, in some sense, the motivation behind my I'm brushing numerical issues under the rug apology at the beginning. So the real answer is that yes, so Chebyshev polynomials that we'll write down, they have coefficients that explode, and that actually causes very bad numerical issues if what you do is write your Chebyshev polynomial as a polynomial and then multiply and add. That was essentially the content of my apology at the beginning. But instead, we'll see when we write down the properties, they obey a 3-term recurrence relation. And so the right thing to do is essentially to use the 3-term recurrence relation and also tie it back to the residual. So the right numerical way to compute them is to write a couple of the things that are mathematically equivalent involving the right-hand side and the polynomial and the value in the correct way that you don't lose for this stuff that shoots off to infinity. And that's why if you look at a numerical analysis book, the iterative method I'm describing is going to look a bit different, is that there's a way to write it where you're only using the sort of last couple term update, and you're essentially referencing it back to what the actual value of the polynomial is supposed to be so that your errors don't shoot off to infinity. So on the gradient descent side of things, it would correspond to, instead of if you wanted to write a Taylor series for 1 plus x plus s squared plus etc., what you do is instead of calling the monomial, instead of getting that by multiplying it by the matrix a whole bunch of times, you're going to use b minus ax as a way to kind of tie it. You're going to do the gradient descent when you tie it back to the actual right-hand side. You're going to use the residual instead of the polynomial. And you can do the equivalency here. So yes, that's why there's a complexity. These coefficients do go horribly haywire. Thanks. Okay, so once we have that, this is what we're going to do. We're just going to sort of just shift and translate it. So I'll define a linear map that's just going to this is the lambda 1 and lambda n. And all I'm going to do is just kind of flip it around. So this linear map here is just the thing chosen so that it maps lambda n to -1, it maps lambda 1 to 1, and then it maps 0 to whatever it's forced to map 0 to. And the point is that we're going to hope that when we do that, if there's a big gap here compared to the scale here, this will have time to blow up and get very big at 0. And then so that's what this linear map does. That gives us a polynomial that is hopefully much bigger at 0 than it is in the interval. And then we're just going to scale it down. So instead of being big and small, it's 1 and small. Right? So the numerator here is just take your Chebyshev polynomial and finally change it to map the eigenvalues to the interval. And then we're just going to divide it by its value at 0 to make it be 1 and small as opposed to just two numbers that are far apart. So that will be our construction. And so I claim that when my animation seems to have horribly gone awry, right? Wow, something's stalling. Okay, so let me figure out what's going on in the computer. I think it's actually just maybe my computer's just being slow. So
Those big coefficients.
awesome. If you can see my screen now, it's telling me that PowerPoint camp is not responding. Ooh, wait, there we go. Okay, so yeah, let me just keep them so it doesn't break. So okay, so the point is that I claim it has the properties I've asserted, and meaning that if I gave you, why is this breaking so badly? Okay, so this is really not good. Okay, so it's going to have the properties I asserted, and they're easy to verify. And if I can get to my previous slide, I will show them to you. Wow. Is there anyone from Microsoft here? Sorry. Okay, so the point is just that if I look at this, what's actually happening? It's so inside the interval, now that I've given you the slide enough times, I guess you can just kind of look at it. So for lambda in the right range, it's mapping the interval here, and then this blowing up property is making the value 0 much bigger. So if you were to look at qk of y, we get that it's we get that the denominator is going to be pretty big and the numerator will be pretty small, and we get exactly the behavior we asserted. Okay, so this was easy. The harder part was getting the polynomials that actually do any of this. Right, so any questions other than whether I should have publicly bashed Microsoft, given that I have lots of friends who work there? Yeah.
So did you need to know lambda 1, lambda n, etc., or just
Yes.
k of kappa?
That's another good question. So the conjugate gradient method, which is not what I'm doing, manages to get away with not knowing them, and it performs. So if I told you those, then this would perform it. Then conjugate gradient. Sorry, if I didn't tell you though, conjugate gradient would perform as well as an S polynomial, so it might as well know them. Here, what I'm doing requires you to in advance know them. The reason I'm doing it is that later conjugate gradient is not going to be, it's going to lack certain properties that we'll need for numerical precision in the next lecture. And so we want a fixed polynomial, and we will in the linear system, in the Laplacian case, actually have the bounds that we need.
So you need to know what lambda 1 and lambda n in
Or at least
the first order method, you only needed kappa, right?
Yes, so so for both of these you need to know bounds on lambda 1 and lambda n. Okay, so Chebyshev polynomials. So there's a couple definitions of them, and I'm going to write 3 of them, and then gesture at them to say why they have the properties of them. So the one that I think is the kind of most intuitive one is the trigonometric one. And what you should be thinking here is, really we're doing Fourier analysis, but on a slightly under a change of variables. So the definition that I think is the cleanest to work with in a lot of these cases is think of tk as the polynomial for which the following holds. And I should note that this is not obviously a polynomial. So what you'll look at is you'll say, I'll look at cosine of k theta, and then I'm going to assert that that's a polynomial in cosine theta, and the Chebyshev polynomial is the polynomial with that property. So it's the polynomial such that this holds. So it's cosine of k. Yeah. I can't blame PowerPoint for that, can I? So it's cosine of, let's say k, or cosine of x. And it's not obvious this is a polynomial, but it is obvious that it's nice, right? Because if you look at it, what we're really doing is Fourier series under the change of variables where we just take a cosine. Okay, so why is this a polynomial? Well, the easiest way I know to verify it's a polynomial is to note that cosine is going to obey the following recurrence, and then pretend that I define the polynomials with the recurrence, and they're the same thing. So definition 2 is the following are my Chebyshev polynomials, and I assert that it's a very easy verification that they match my previous assertion. Right, so I'll define t0 to be 1, t1 to be x, and tk to be this recurrence, 2x, tk of x minus tk negative 1 of x. Okay, so it's just a double angle identity, or whatever the version of that with k and k plus 1 is, to verify that it obeys these recurrences. And then we've now convinced ourselves that it is a polynomial. Now, once we have both of these, there's an even nicer one to work with for one of our bounds, and that's going to be an explicit form for them, which I think I could have just written down from scratch, but I think it's a little unmotivated, which is this. So it's just the right way to convert one to the other is if you write cosine theta as e to the I theta plus e to the negative I theta over 2, and then just plug it into the first one, it's not very hard to get this expression. Okay, and that's what we'll use just to verify the bounds in a second. Okay, so those are our 3 versions of Chebyshev polynomials. Because I'm running slow, I will not prattle on too much about what I think they really mean, but I will convince you that they're true and satisfy the properties we need to get a good algorithm. So those are the properties I said that they're supposed to have. They're supposed to be small between -1 and 1, and they're supposed to be big when you leave the interval. Okay, so I claim these are immediate from the appropriate choice of these 3 choices of definition. So property 1 I claim is immediate from the trigonometric definition. Right, I want it to be between -1 and 1 when x is between -1 and 1. But note that when x is between -1 and 1, our cosine makes sense. And I'm just taking cosine of something. And so the something is going to have a cosine that is between -1 and 1 because it's a real number. Okay, so that one was trivial, and that was why I got these little zigzaggy things. That was more or less what this is a slightly transformed cosine. And so that's the squiggles, and note that the number of times it turns around will just be up to a plus or minus 1 will be the degree of the polynomial. Okay, so property 1, that it stays bounded inside the region, is easy. And then property 2, the blowing up one is going to follow immediately from the explicit formula, right? So if you just ignore the second term, the explicit formula is certainly bounded below by this. And then note what was the point here. The point was, well, if I plug in something bigger than 1, then I'll get at least 1 here, and then I'll get something that's, well, bigger than 0, and I'll raise it to a high power. So if we extend it out, what do we get? We get tk of 1 plus a, and I'll just plug that into our formula. And then if you just kind of write out what's inside there, you get 1 plus a, and then you get 2a plus a squared. And then you're just going to ignore a bunch of terms.
Where did the power
Little t is k.
T is supposed to be k.
Damn it, Microsoft. That one's my bad. So k and t and maybe n, we should all be the same letter. This is a different changing notation at the last minute. Or writing your talk in the last minute. Okay, so thanks. Good. So, right, so anyway, the upshot was you just start erasing terms and keeping the one, and you end up with a fairly easy assertion proof of your bound.
Make a small comment there. There is a fourth way of understanding Chebyshev polynomial. Let's say I normalize the leading term to be monic, so it's 1. And then you want the polynomial of this sort that is the best L infinity approximation to the 0 function in the interval -1.
Right.
And then it goes like 2 to the minus k. And that is perhaps a good way to understand why exactly this is the polynomial that worked for you here. Because this is precisely what you'd like to accomplish.
Right, so this is, just to restate that. The property I wrote down was a scaling of the assertion that is, so if I scaled this down or up, I would get that assertion, and you could just ask for the L, you want to get as good an L infinity of, well, exactly what you just said. The reason I didn't do that is I didn't know a very short proof that these are the polynomials that you get, other than going through roots and interpolation and stuff. Like I didn't know a way to take that and can construct Chebyshev polynomials from it. It was an easy way to verify that they are right once you guess them. I didn't know a way that didn't feel magic to write
There's
it
a
down.
very short tool, but you do some convex duality, and you show just because they meet, they're equal to plus minus epsilon in all these points. That's a
Right. So
this constitutes a proof that
it's a proof that they are optimal once you guess them.
Right.
It takes a little bit more. I actually thought about putting that one in, but the reason I cut it was that I couldn't think of a motivated way to guess them without, but that's, yeah, so the assertion is that you actually, there is a principled way of deriving what the right answer here is, which is that we're putting some infinitely many linear constraints on a polynomial. We have a constrained optimization problem. We'll find the best polynomial to be one and big and in the interval and small and in the other places we want it to be small. And you could just then write down this infinite dimensional LP and solve it. And then it's a way to verify that Chebyshev polynomials are actually optimal for the construction we're getting here once you have them. It says that essentially the property you want is that I have something that oscillates and you want all of these extrema to, you want to have as many extrema as your degree can tolerate, and you want them to be as small as possible. And then you can actually see that that's just the existence of a dual certificate for the optimization problem. Yeah, I probably, well, if I have, maybe I'm already 5 minutes over, so let me finish up this and then I'll be happy to give anyone offline, I'm happy to give the longer version of that. Okay, so the upshot of all of this was that we now got our promised result, which was, given a condition number, we can actually solve linear systems in something that depends only on the square root of the condition number. So given any linear system, we have a simple iterative method that you can get to error epsilon in something that's like root kappa times log 1 over epsilon matrix vector multiplies. The square root savings will be something we'll use next lecture when we do Laplacians to actually get the right running time that we want. You'll get something a little worse if you don't. You won't get something quite as good if you just try to use the linear, if you didn't have a square root there. Note that it did require the bounds that we asserted, and as I've sort of promised, there is an algorithm conjugate gradient that will perform as well as the best polynomial. It more or less is just taking a set of orthogonal polynomials in the appropriate norm. It's a little harder to use, and I don't know how to get the numerical analysis for the recursive preconditioning to go through for it. And so the nice thing about Chebyshev is it's a fixed polynomial, which means that you can control the errors in a different way. You can take advantage of the fact that it's a fixed polynomial. But conjugate gradient will, in a infinite precision world, will perform this as well. Again, something that's worth noting is that when you have clustered eigenvalues, there are polynomials that do better. The thing we wrote down was the optimal answer for only assuming a biggest and a smallest bound. If I have nice little clusters somewhere and I know something about the structure, you can certainly get polynomials that are smaller or better using that structure. Then the last thing I'm going to say, and we'll talk about it in depth next lecture, is that this is not always dask. It's a function of kappa. And when kappa is bad, this is terrible. Right? It's very slow when things are ill-conditioned. And unfortunately, Laplacians are ill-conditioned. So my final assertion of the day is going to be that Laplacians are often ill-conditioned. And the easiest way to see that is going to be the path graph. So if I give you a path, I think Luca said, it's the ratio of its biggest to smallest eigenvalues is actually going to be n squared, the number of vertices squared. And so that would say that what we'll need here is square root of n squared, so n iterations to solve a Laplacian system with a path graph. And so that certainly won't give us a linear time algorithm. And so in some sense, what you can interpret a lot of the other stuff that's going to come later is going to be sometimes that's going to be our only obstruction. And if you want to take a couple hundred pages of recursive preconditioning and reduce it to a paragraph, I think the paragraph I want to say is that if you really take care of paths, everything else is fine. And the two algorithms we'll present will be two very different ways of taking care of paths. So next lecture, we're going to talk about how to do it with recursive preconditioning. And the lecture after it, we're going to talk about how to do it with sort of building a different basis for the space of functions that you're working with. Okay, so that sort of concludes my background stuff. Starting next lecture, I'll actually give you things that were in the last 40 years. And so next lecture I'll do is talk about the algorithm by Kudus-Miller-Peng. That will give you an actual, almost fully proven on slides, modulo my inability to type letters, proof of a newly linear solver. And then after that, I'll give one that doesn't use any of the preconditioning. Okay, thanks. Questions? Yeah. Oh, so the reason was that the what we were gonna, so the property that we were really shooting for was a polynomial that was 1 at 0 and small between lambda 1 and lambda n. And so we mapped negative 1 and 1 to lambda 1, and then that was the biggest zero part of it. Okay, I think maybe I'll take other questions offline just because I think I've run a little over, but I'm happy to answer any questions you may have.